Thank you to the Simons Foundation and the Flatiron Institute. I'm very grateful for the invitation to be here today. Following on David's remarks, this business is not for the faint of heart, and I hope to share with you today a bit of the science, the physics and chemistry of the ocean worlds of the outer solar system and some of our path forward for missions to explore these worlds. Humans have been exploring our solar system with robotic vehicles for a little bit over 55 years now. And this beautiful diagram created by National Geographic shows a line for each of those robotic spacecraft heading out to the many worlds beyond Earth. You see many lines to the moon, to Venus, to Mars. The deeper color, the higher contrast colors indicate successful missions. The more muted colors are for missions that failed for one reason or another. What you see in this diagram is that there's just a few lines that go beyond the asteroid belt. These are lines that represent spacecraft with names like Pioneer and Voyager and Galileo and Cassini. And one of the lesser appreciated discoveries from our robotic exploration of the solar system is that by merit of those few spacecraft, we now have good reason to predict that oceans exist beyond Earth. These are liquid water oceans that are there today. And in some cases, these are oceans that have persisted for much of the history of the solar system. This is what I like to call the portrait of ocean worlds of our solar system. At the center, of course, is the Earth, the planet with the ocean that we know and love and need to protect. And around the Earth, I've placed Europa, Ganymede, and Callisto, three of the large moons of Jupiter, which are covered in ice, and beneath their icy shells, we think there are global liquid water oceans. I've got Titan and Enceladus there, two moons of Saturn, both of which we think have liquid water oceans. In the case of Titan, it also has this nice thick atmosphere. And I've even got Neptune's curious moon Triton here, which may have a liquid water and ammonia ocean. These ocean worlds, these ice-covered moons of the outer solar system that harbor oceans, are really changing our understanding of what it takes for a world to be habitable. In the early days of planetary science and astronomy, we had this framework for habitability where the habitable zone was defined by your planet being at just the right distance from your parent star. If you were too close, like Venus, you were too hot. If you were too far away, like Mars, you were too cold. But if you were at about the Earth-Sun distance, then you were at just the right temperature so as to sustain a liquid water ocean in contact with a nice thick atmosphere, and you could harbor liquid water on the surface. Now, of course, the story is much more complicated than just distance from your parent star, but this kind of represented the habitable zone in this Goldilocks scenario. Too hot, too cold, and then just right in the middle. What these ocean worlds of the outer solar system are teaching us is that this is an old Goldilocks. There's a new Goldilocks for habitability, and it's one in which the energy for maintaining and sustaining liquid water comes not from the energy of your parent star, but rather from tidal dissipation, the tidal tug and pull as these moons go around their giant primaries. And there's no better example of this relationship than the Jovian system, and in particular Io. Io does not have an ocean, but Io is the most volcanically active body in our solar system. This image here shows a volcanic plume erupting near the North Pole of Io. There are volcanoes erupting on Io right now. It is more volcanically active than the Earth. And so in this sort of new Goldilocks for habitability, Io is kind of like Venus. It's got too much tidal energy dissipation. It lost much of the water that it may have once had. Callisto, even though we predict that Callisto does have an ocean, its ocean is primarily maintained through the decay of heavy radiogenic elements, and as a result of not having much tidal energy dissipation, the ice shell of Callisto is likely very thick and very old. In the middle, however, we've got Europa and Ganymede, and Europa in particular may occupy this new sweet spot for habitability, this new Goldilocks zone, where it has just the right amount of tidal energy dissipation so as to sustain this liquid water ocean in contact with a rocky seafloor beneath a relatively thin ice shell. And when I say relatively thin, I mean a few to as much as 20 kilometers in thickness. To put that in reference, the Antarctic ice sheet is about 4 kilometers thick. Now, there's another component to this Goldilocks. Having liquid water is not enough to be habitable. You also need to have the elements and the energy needed for life. And here's where our solar system gets kind of interesting. When you look at the periodic table and the elements that life needs, there's a suite of essential elements, the chnops, the carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, and then a smattering of roughly 58 other elements that life as we know it needs. And if you were just to look at the periodic table and just to look at our solar system, you would conclude that despite evidence to the contrary, planet Earth is a bad place for life. Earth did not start out with much water, it did not start out with much carbon, and yet, of course, we know that Earth is beautifully habitable. But what do I mean by this? Well, if you think about the solar system formation and the pressures and temperatures throughout the solar system, in the early days, a lot of these light elements were contained in volatiles like methane and ammonia and CO2, et cetera. And those light elements condensed out at various points in the solar system, various snow lines. This is a very complicated plot. Let me simplify it by just sort of blanking out a few of those lines. Here I'm showing you temperature versus pressure. This essentially is giving you the condensation points for various key volatiles. So if you're below the line, you're in gas phase. If you're above the line, you're in solid phase. And so a lot of these compounds that have carbon and nitrogen, sulfur, et cetera, they were in the gas phase and not well trapped by planet Earth in the early days. Even water, we have more water than makes sense for the Earth. We think that much of the water that we now have likely came from comets after the Earth settled down. But these moons of the outer solar system, they formed in cold regions of our solar system where they could easily accumulate and accrete a lot of these volatiles with the light elements that are needed for life. What about the heavy elements? Well, here's another part of the Goldilocks story. Not only do you need tidal energy, not only do you need to form in a region of the solar system where these volatiles can condense, but you also need to have a decent fraction of rocky material. Going back to that periodic table, we need iron, nickel, a few other things. And so even though the volatiles are important, you still want to have some silicates. You still want to have some rocks. And this plot showing the radius of these moons as a function of density is illustrative of that relationship. When you plot the various moons of the outer solar system on a figure like this, you get these sort of clusters. Down here, you've got the small to medium-sized icy satellites. These are relatively low density. If you're too low in density, like Mimas, you are basically a big ball of ice and perhaps don't have some of the heavier elements that are needed for life. Enceladus, as I'll get into later, I think has just enough of a high density so as to have trapped some silicates and to have a water-rock interaction where you get the water leaching out some of the heavier elements. Up here, we've got the rocky satellites, and Europa is classified as a rocky satellite. Its mass is about 3,000 kilograms per cubic meter. And it may be that, that Europa actually lacks an excess of carbon or nitrogen. Forming where it did in the Jovian system, it may not have actually trapped much methane or ammonia. Ganymede, Titan, Callisto are all in this class of large icy satellites. And here's where another curious thing happens. If you get to be too big of a moon, then you've got an ice shell of, say, ice 1, the kind of ice that we know and love and we have in our freezer. So you've got an ice shell, and then you've got an ocean, but then the pressure at the bottom of your ocean gets to be so high that you start to form higher phases of water ice. And so on these worlds, it may be that their seafloors are of water ice of a higher phase, ice 6, ice 3, ice 4, ice 5. And so you might not have much water-rock interaction in the case of these moons. And so you go too far up here, you might have too much rock, too little ice. You come down here, you might have too much ice, too little rock. And if you're out here, you might end up with icy seafloors and not enough water-rock interaction to help supply those heavier elements. And so when we think about the kind of keystones for life, life as we know it needs liquid water, it needs the elements to build life, and it needs some form of energy, some chemical disequilibrium through which it can get the work of life done. And I'll get into that a bit more later. And so when we think about these ocean worlds of the outer solar system, really what is so compelling is that it is within these moons that we have a great abundance of liquid water. And if we've learned anything about life on Earth, it's that where you find the liquid water and those elements and some form of energy, you generally find life. Whether it's life in extreme environments like hydrothermal vents, Antarctica, Rift Valley, hot springs, whether it's life in extreme environments or life of extreme lifestyles, all life on Earth requires liquid water and those elements and energy. But I like to show this image for another reason, and that is that it helps to emphasize one of the key points about the value of exploring these ocean worlds. For all of the diversity of life on Earth, from the most extreme of microbe at the depths of our ocean to the craziest of rock star, all of life on Earth is connected by the same tree of life, the same genetic tree assembled from 16S RNA. And think about it, just 60 some odd years ago, this was our tree of life, connecting Neanderthals and dinosaurs to humans and trilobites. Since that time, we now know that all of that life is just a tiny twig on this bigger tree of life. And even this tree, showing the archaea, eukaryotes, and bacteria, has come a long way in just the past 20 some odd years. This is the most recent tree of life from 2016. And part of what compels me and my colleagues in the search for life within ocean worlds of our outer solar system is this question of, do other trees of life exist in our solar system? Is the origin of life easy or hard? Do other biochemistries work? Or is the DNA, RNA, protein, ATP paradigm the only game in town? What is the role of biochemical contingency versus convergence when it comes to biology? And so when we think about these ocean worlds, it really gives us the prospect of potentially finding second origins of life, probing this question of whether or not the origin of life is easy or hard, and potentially seeing whether or not there are trees of life beyond Earth. And to really probe that question, you need to go to places where life could be alive today. This is in sharp contrast, for example, to our search for life on Mars, at least our current search for life on Mars, where we're looking for evidence of life as recorded in the rock record on Mars. Large biomolecules like DNA, RNA, et cetera, don't survive for a long time in the rock record. To probe the question of life's biochemistry, we need to go to places where life could be alive today and we could actually sample it. So here's a summary of these ocean worlds, and throughout this talk I'll go into some detail on the columns to the right. These are the 6 worlds that I showed you at the beginning. There may be a few other moons of the outer solar system that could be added to this list. There are certainly some moons that we think may have had oceans in the past, but may not have them today. You can first ask, is it geophysically and geochemically plausible? Does it have significant tidal energy to help maintain that ocean? Is there an induced magnetic field that tells us that the ocean is there? And I'll describe that in a little bit. Do we see any sort of activity associated with the ice shell and its interaction with the ocean below? And I'll go into some detail on that. But for the moment, I just want to draw your attention to this last column. Is there a water-rock interaction? Because when it comes to habitability, really two moons stand out: Europa and Saturn's Enceladus. And then if I had to prioritize even further after this role of a water-rock interaction for habitability, I would say that time is a key factor. When it comes to Europa, we think its ocean is there today, and we think it's been there for much of the history of the solar system. In the case of Enceladus, the story is not quite fully developed yet. There are some models that show that perhaps Enceladus may have formed subsequent to a Kuiper Belt impact event in the Saturnian system as recently as a few 100 million years ago. And when we think about the origin of life and habitability, time is probably something you want more of. And so for Europa, I think it may qualify as persistently habitable, whereas with Enceladus, we're still trying to figure that out. Now, it may be that 100 million years is fine for the origin of life, and so that time issue is really not that big of a deal. But selecting one at the moment, I would prioritize Europa. So the surface temperature of these moons is in the ballpark of 100 Kelvin, minus roughly 280 degrees Fahrenheit. Neither Europa or Enceladus have atmospheres, so you're basically going from that very cold ice into the vacuum of space. The oceans themselves, the liquid water, is somewhere near the freezing point, 270 Kelvin. And now there may be, depending on the salinity, a certain depression of the freezing point down to perhaps 260 K, maybe 255 or so. But for the most part, if we assume steady state, which may be a flawed assumption, the liquid water is touching these ice shells, and so it's got to be somewhere close to the freezing point. So let's go to Enceladus. This is Enceladus with Saturn in the background. One of the rings can be seen there. Enceladus is a curious moon. It's only about 500 kilometers in diameter. It's shown here relative to the Great Lakes. And one of the first things you see when you take a close look at Enceladus is that it's got this bizarre dichotomy. The northern hemisphere, the ice of the northern hemisphere, is pockmarked with all of these craters. The south has essentially no craters. To a planetary scientist, this is revealing of the surface age. Craters indicate that a surface has been around for a long time. In the case of Enceladus' northern hemisphere, these craters give us an age dating of about 3.5 billion years. Meanwhile, the paucity of craters in the south gives us essentially a zero surface age for that region. And if you look even closer, you see these 4 parallel fractures that have come to be known as the tiger stripes. These fractures were investigated in great detail by the Cassini spacecraft, and the brilliant engineers at JPL who do the orbital dynamics and trajectories of the spacecraft managed to take an absolutely astonishing picture of Enceladus with just the right angle from the sun so as to capture these fractures and what's jumping out of the fractures. Okay, good, good. Sometimes I heard a few oohs and ahs. Sometimes I have to prompt the audience. So this, what you're looking at here are those fractures in the ice, and out of those fractures are these jets, and these jets contain water, and as I'll show you, a bunch of other compounds that are indicative of a potentially habitable ocean with a water-rock interaction. Here's another stunning image, and what I love about this image is that you can actually see, so the sun's down over here, and the shadow of Enceladus is being cast and projected onto those plumes. And so the plumes themselves serve as a screen onto which the shadow then can be seen. So the Cassini spacecraft passed through these plumes and was able to sample this material with 2 mass spectrometers that it had on board. The Cassini spacecraft, of course, finished its mission this past fall. It went into this beautiful proximal orbit sequence and eventually dove into the atmosphere of Saturn and that was the last we ever heard from Cassini. But before that, it had many great years sending back data, not just of Enceladus, but everything in this Saturnian system. But when it comes to Enceladus, the mass spectrometer, the two mass spectrometers, the on and neutral mass spectrometer and the cosmic dust analyzer, told us about the composition of these plumes. One of the first data sets to come back was from the on and neutral mass spectrometer, which showed that not only do those plumes have water vapor, but they also have methane, carbon monoxide, carbon dioxide, and then a curious collection of simple organics and complex organics. Now the mass spectrometer, that mass spectrometer stopped at 100 AMU, 100 Daltons. In other words, it wasn't able to go high enough up to really give us some of the detailed chemistry, nor was it designed to. There were some hints that Enceladus was going to be interesting prior to the Cassini mission, but really the mass spectrometers on Cassini were designed to sample the upper atmosphere of Titan. And so we sort of serendipitously ended up with these instruments that were very valuable for the plumes on Enceladus. But these complex organics and simple organics were very exciting. In the early days, though, there were some of us that said, well, as exciting as those organics are in the context of habitability and life, there are other things that have jets and organics. Those are things like comets. You look at the comet and you see all sorts of organics. So this, even though it was compelling, was not a smoking gun per se for a liquid water ocean with a water rock interaction. That evidence in part came a little bit later with the cosmic dust analyzer, another mass spectrometer wherein it's a time of flight and these dust particles from the plumes ram against a plate and then are collected and analyzed. And from that data, it was revealed that there are these sodium chloride and sodium hydroxide salts in the plumes. And it's really hard to explain salts in a water solution without there being some sort of rocky silicate seafloor through which the water can leach and extract those salts. And then subsequent to that, that same team also reported on identification of silica, SiO2, in the ice grains that emanated from the plumes. Why is SiO2 interesting? Well, in order to get SiO2, you really need some sort of water rock interaction that essentially amounts to low temperature alkaline hydrothermalism, an active seafloor that perhaps has hydrothermal vents. And so for me and many of my colleagues, it was this combination of the salts plus the SiO2, and more recently actually a hydrogen excess, that has led to the current model where we've got an ice shell with fractures in it. And this ice shell might be about 30 to 40 kilometers thick, maybe much thinner in some places. That's underlain by this ocean that's tens of kilometers in thickness, and then this relatively porous seafloor that may be powering an exothermic geochemical reaction that we call serpentinization. To give you one example of that serpentinization and what we think might be happening within Enceladus, this is some video shot at the bottom of our own seafloor at a locale called Lost City. Lost City is not along one of the axial spreading ridges. This is a place where the oceanic crust is cracking and water can seep into that oceanic crust and drive this reaction where the ultramafic, the heavy mantle material, is essentially oxidized by the ocean water. And from that comes hydrogen gas, methane, carbonates precipitate. And so we see on Earth these serpentinizing sites that don't necessarily require vigorous plate tectonics. And yet here on Earth, they do drive very dynamic ecosystems. This is our current cross-section for Enceladus. A relatively porous, not entirely differentiated core and mantle region. That global liquid water ocean, this ice shell, and then to the south, at least these fractures that are allowing the ocean to erupt out into space. We now know that the ocean is global. For a while there, it was thought that it was just a South Polar Ocean. We know the ocean is global because of the libration of the ice shell. The ice shell wobbles back and forth, and the magnitude of that libration is too strong for it to be a solid all the way through. Our moon librates, and our moon is solid all the way through. But if our moon, for example, had an ocean and a disconnected ice shell, that libration would be a lot larger. And so through careful analysis of the motion of the ice shell, it was determined that it had to be disconnected from that seafloor. This is a mosaic of Enceladus at the highest resolution that we achieved with the Cassini spacecraft. This is about 6 meters per pixel. This is sort of an airplane flyover of that cracked and fractured ice. If you could dive down into one of these fractures, you might be able to pinball your way all the way down through that ice to reach that ocean below. And we actually do some studies at JPL and within the broader NASA context. We have done some studies on what it would take to send a robotic vehicle down into this ice with various tethers and ways to get the data back up and how you would navigate and negotiate this incredibly fractured surface. So someday, decades from now, I hope we do put a lander on the surface that can get into these fractures. I want to move to Europa now. Europa is a much larger moon than Enceladus. It's about the size of our moon. And yet it orbits Jupiter, which is some 318 times as massive as the Earth. And as a result of that tidal interaction, Europa's icy surface is cracked and fractured in ways that are perhaps similar to Enceladus. But with Europa, there is no obvious dichotomy. The entire surface of Europa essentially lacks craters. And with the few craters that have been identified, the globally average surface age of Europa is set at somewhere between about 10 and 100 million years old. To put that into context, that's comparable to our oceanic crust. In other words, that is exceedingly geologically young. This is our current model for what Europa looks like. A differentiated core, an iron core, a rocky silicate mantle, an ocean of about 100 kilometers in thickness. It's a global ocean, and then overlaying that is this relatively thin ice shell. And the colors there indicate this perhaps convection within the ice shell that brings oceanic material up to the surface. And so we think that Europa's ice shell might be thin enough so as to provide a window into the ocean below. This is what Europa looks like up close. Again, about 6 meters per pixel. This was taken by the Galileo spacecraft, which orbited Jupiter back in the late 1990s and early 2000s. Here again, it's an airplane view. This is a grayscale image. Everything that is white here is water ice. The gray and blacks, that may be salts from the ocean below, might be some sulfur from its neighbor Io. But this cliff, for instance, is about 200 meters high, and the talus that's coming off of this slope could provide some indications of the chemistry from that ocean. Some of these talus blocks could have European squid in them, in my dream of dreams. But how do we think we actually know that Europa's ocean exists? When the Galileo spacecraft flew by Europa, there was not any obvious sign of plumes. There was not obvious new cracks being formed. The evidence for Europa's ocean is quite a bit more subtle, yet in my opinion, it's actually just beautiful and very solid physics. I like to break it into 3 easy pieces. The first piece of the puzzle is to find a rainbow connection. Using spectroscopy, scientists were able to determine that Europa's surface is made of water ice. The second piece of the puzzle, once you know that the surface is water ice, is to babysit a spacecraft. In this case, the baby was the Galileo spacecraft, and the babysitter was the Deep Space Network. By carefully tracking the trajectory of a spacecraft, you can get at the the gravity signature and the interior mass distribution of that world. So with the gravity data, it was determined that there's a water layer in either ice or liquid phase that extends down to about 100 to 200 kilometers. The density resolution of the gravity data was insufficient to determine whether it was ice or liquid. The final piece of the puzzle, I like to make the analogy to adhering to airport security. And this is a picture that I took of airport security at JFK Airport. I apologize that it's fuzzy. I was trying not to get arrested. But when you walk through one of those doorways, as many of you appreciate, you're walking through a time-varying field. And if you've got a conductor in your pocket, that time-varying magnetic field gives rise to electric currents, induced electric currents within the conductor. Those induced electric currents then give rise to an induced magnetic field. And there are sensors around the doorway that detect that induced magnetic field, and the alarm goes off if you've got a conductor in your pocket. Well, when the Galileo spacecraft was flying by Europa, the alarm went off. It detected an induced magnetic field at Europa. How could that be? Well, it's the Jovian system. Well, and so with that induced magnetic field, the data revealed that it had to be near the surface. And the induced magnetic field, just like in airport security, required a conducting layer. And the best explanation for this near-surface conducting layer is a salty liquid water ocean. So these are the three pieces of the puzzle, as I like to show them for explaining the physical basis for evidence of Europa's ocean. Just to go into a little bit of detail on the magnetic field signature, here's a diagram. I got a number of fancy, beautiful pictures. This is not one of those. I drew this up long ago on a transparency and then scanned it in at some point. But it tells the story of how Jupiter's magnetic field and Europa interact. And again, this is just beautiful physics 101. Here's Jupiter, as you can clearly tell by the red circle. And then here's Jupiter's magnetic field with the butterfly. Here's Io, Europa, Ganymede, and Callisto. Jupiter's magnetic field is tilted by about 9.6 degrees from the rotation axis. Jupiter is rotating once every 10 hours. Its day is 10 hours. That's 11.2 hours synodic to Europa. But as a result of this tilt of the B field, you then have the breakdown in the vector components of the B field, and you see that there's an XY component to Jupiter's magnetic field that creates this time-varying, this dB/dt. And so if you're Europa here, at one point in time, the field looks like this. Half of a spin of Jupiter later, it looks like this. And so that dB/dt gives rise to the electric currents, which then give rise to the induced magnetic field. And so it's just a beautiful, Maxwell's equations, Faraday's law, all folded into one. There's another component associated with Europa's elliptical orbit. Saturn, going back out to Enceladus, Saturn's magnetic field is almost perfectly aligned with its rotation axis. And so a lot of this physics was not possible at Enceladus. And so Jupiter was quite generous. Okay, before I move into more detail on Europa, I do want to give a little bit of a public service announcement. Being at the Simons Foundation and the Flatiron Institute and researching the goals of the foundation and institute, obviously there's a push on big data, computational capabilities, and I just want to make this audience aware of the planetary data system. This is, you go to pds.nasa.gov. Every instrument from every mission has been required to store its data in the PDS archive. Now, that's not to say it's a perfect archive. Different instruments have all sorts of different calibration routines, and those images that I showed you of the surface of Europa, those were collected on a magnetic tape, and I don't know who the last person was to fully process the raw data on many of these old instruments, but it's there, and I encourage many of you who are inclined to access these archives to go and explore what's out there. This is the treasure trove of the solar system. So how do we think we know that, that Europa has an ocean that's interacting with a rocky seafloor? Well, that induced magnetic field implicates a salty ocean. And so the fact that Europa has that induced field and requires salts tells us something about a water-rock interaction. But Europa's surface may also be telling us something about the ocean below. And there are many different facets to the compositional story of Europa, and I'll only go into one that this afternoon. This image is about 300 kilometers wide. You're looking at this fractured surface of Europa. We do not have a good understanding of how often these fractures form, what exactly determines where a fracture forms. There are many good models for tidal forcing of some of these arcuate structures. Some of these features are extensional bands that look almost like spreading centers on the bottom of our seafloor. Other features look like freckles and upwelling regions. We call those chaos regions. And so for just about every feature on Europa, there is an equivalent model, and we really just need to get back out there with more capable spacecraft to figure out what's going on. But I want to draw your attention to the colors here. The white and blue is, for the most part, we think water ice. And then this reddish brown and even sometimes yellowish material has been the topic of much debate. The Galileo spacecraft had a visible and near-infrared spectrometer on it, but the spectroscopic resolution of that data was insufficient as to require salts as an explanation for that material versus sulfuric acid. Sulfuric acid? Where the heck does sulfuric acid come from? Well, Io, remember, is the most volcanically active body in the solar system. It's erupting a bunch of sulfur out into the Jovian plasma. Some of that sulfur then hits Europa's surface, and then the radiation processing of that material leads to the generation of sulfuric acid, H2SO4. If this discolored material is sulfuric acid, then it's not from the ocean below, it's from Io. If, however, this discolored material is a salt, then it's a window into the subsurface. So with that in mind, my colleagues and I did a few different experiments. We've also used some of the Keck, we've used the Keck telescopes to also get at this. But for today, I just want to share with you a little bit about what we've done in the lab. This is our Icy World simulation facility out at JPL. And in this facility, we build these ultra-high vacuum chambers where we've got a vacuum inside, a cryostat to cool it down so we can get to Europa temperatures and pressures. We then have infrared spectrometers looking at the sample, mass spectrometers looking at the sample, and then an electron gun to bombard the ice that we put into the chamber or whatever other materials there are. And that electron gun serves to replicate the roughly 125 milliwatts per square meter of charged particle bombardment that Europa gets from the Jovian magnetosphere. So in this case, if Europa's ocean is salty, there's good reason to predict that it should have sodium chloride, similar to what our ocean has. There's lots of geochemical rationale for that, and I won't belabor those points. But suffice to say that if it's an ocean interacting with the seafloor, there should be sodium chloride. Unfortunately, sodium chloride, as you know from your dinner table, is sort of a flat white, and spectroscopically, it has essentially no features. And so even if there were pure sodium chloride on the surface of Europa, we would not be able to see it spectroscopically. The caveat is that if you've got irradiated sodium chloride, then some new features appear. And so what we did, we put sodium chloride into the chamber, turned on the electron gun, cooked it under Europa conditions, pulled out the cryostat, this little cold finger that you're seeing here, and that sodium chloride turned to this caramel brown color. And what's happening here is that within the alkali halide lattice, you're trapping electrons in the anion vacancy. It's another just beautiful little consequence of radiation physics. In doing these experiments, I went back to actually a bunch of work that was done during the Manhattan Project days on radiation of materials at Los Alamos. And so by having these trapped electrons within the lattice, you darken the material and you also generate some very strong spectroscopic features. Now, we don't expect Europa to have these nice crystals on the surface. We expect Europa to have sort of an evaporite. So we did that experiment too. This is looking inside the chamber. This is a solution of sodium chloride that I made and then put inside the chamber, and then sublimed and essentially pumped out the chamber to leave behind an evaporite. This is what that evaporite looks like under irradiation. I've rastered back the electron gun here so you can actually see it moving. And so that evaporite that you see on the target there underwent irradiation similar to what it would have experienced on Europa. And here again, when I pulled it out of the chamber, we saw this discoloration, a discoloration that looks somewhat similar to that yellowish brown, reddish brown that we see on the surface of Europa. Unfortunately, there are no really good spectroscopic data in the visible region of the spectrum where you form these color centers. But using the Galileo data, we did a bit of a comparison just to show that our spectra in the visible region where you get these color centers associated with those captured electrons, these color centers appear at 460 nanometers, 723, and perhaps a little bit at 830. This is the brine, the grains, and then for comparison up here, NaCl grains, no irradiation, just nice and flat. Magnesium sulfate, another candidate salt, also quite flat. And then photolized sulfide plus water, pretty featureless. The Galileo solid state imager, these are the filter bands for it, shows some consistency with, it's not diagnostic in any way, but some consistency with our lab measurements. And these filters are from one of those dark reddish brown regions here. So our next step is actually to get better spectroscopic data with ground-based telescopes and perhaps with Hubble to see whether or not our discolored salts match the spectra. So we think that Europa's ocean has a water-rock interaction, these salts leaching out from the seafloor. And so the water is there, the elements are likely there, but what about the energy that's needed for life? These oceans, be it Europa's ocean or Enceladus's ocean, are trapped beneath these thick ice shells, and so photosynthesis is not really going to be a viable pathway for powering life. Really the only option is chemosynthesis, the type of chemical dynamic that helps power life at hydrothermal vents on our seafloor. And what do we really know about the energetic limits for life? Well, the way I like to think of life is that it kind of works like a battery. You've got to have a positive terminal and a negative terminal. In the equations for life, it's always driven by a negative change in Gibbs free energy. I won't go into detail on that, but suffice to say that every metabolic pathway that life on Earth uses takes advantage of a negative change in Gibbs free energy and brings together an oxidant and a reductant, something that wants to get rid of its electrons and something that wants to collect electrons. When it comes to Europa and Enceladus, even if they have active seafloors, those active seafloors may be biochemically insufficient so as to power life. Seafloors with hydrothermal vents, as we know them on Earth, provide only one terminal on that biochemical battery. Hydrothermal vents are very good at supplying reductants. So you can get all the hydrogen you need or perhaps all the methane you need, but if you don't have the oxidant, if you don't have the electron acceptor, then it might be game over for life from an energy standpoint. Well, on Europa, the magnetic field may be the answer to that problem. The magnetic field may solve this issue. What happens on the surface of Europa is that That charged particle radiation bombards the water ice, which then splits into H plus OH, and some of that OH combines with other OH. OH plus OH gives you H2O2, hydrogen peroxide, which then, if irradiated further, gives you H2 plus O2. The hydrogen escapes, and some of the O2 sticks around. And we actually see on the surface of Europa hydrogen peroxide in its surface. And we see with ground-based telescopic observations trapped molecular oxygen, O2, within the ice of Europa. Recently, my colleague Mike Brown and I have used the Keck telescopes to further map out the hydrogen peroxide, and we see results that are consistent with the Galileo data. And the upshot to all of this is that the ice of Europa, as a result of being irradiated, has about a 0.13% by number abundance of hydrogen peroxide. That's roughly equivalent to what you would get if you took the 3% hydrogen peroxide solution that you get at your local pharmacy and dilute it with 3 gallons of water. If that peroxide and also oxygen, which is in the ice, and the oxygen may be there at a level of fractions of a percent to a few percent, if that oxygen then is mixed into the ocean below via geological activity, then you could end up having an oxidant to couple with the reductants from the seafloor. So in the case of Europa, you might have this sort of planetary scale biochemical battery where the seafloor interaction with the ocean gives you the reductants, and the ice shell interaction with the ocean gives you the oxidants. For Enceladus, this balance between reductants and oxidants is still unknown. The radiation of its surface is down by about an order of magnitude from that experienced by Europa, but there is good reason to predict that the ice of Enceladus should have at least some fraction of the oxidants that we see on Europa. So I want to bring things back to planet Earth because, of course, I've been talking a lot about habitability and the requirements for life. But the whole reason we know anything about what to say about habitability and the requirements for life is, of course, by studying life on Earth. And through my work, I've had the great opportunity to be able to explore some regions of our planet where life exists in some considerable extremes, be it Antarctica or near the poles or the depths of our ocean or some of the deserts. And we, of course, find life all around our planet. But there's really only one place that, from a pressure and oceanic standpoint, is comparable to the conditions within Europa's ocean. And that is the Mariana Trench, and in particular, the Challenger Deep. And a number of years ago, I got to be part of an expedition to, for the first time since the Trieste expedition in 1960, send a human down to the Challenger Deep. That human was Jim Cameron, and it was a National Geographic and Rolex, and just an amazing expedition. I have gotten a dive to the bottom of our ocean. The video that I showed you earlier, I was part of that dive. I did not dive on the Mariana Trench, and so when people ask me what did the Mariana Trench look like, I say it looked like this. So this is the Mariana Trench. If you drop a pebble here, it drops for about 11 kilometers. And this was an absolutely phenomenal expedition. This vehicle, the Deep Sea Challenger, was built and constructed in just a relatively short period of time. Contained one person within this sphere. This was one of the test dives. And so James Cameron was in there, went down to the Challenger Deep, explored the bottom of the Mariana Trench for nearly 4 hours, came back up to everyone on the top side's great relief. He did not die. What's that? This is right. James Cameron, the movie director, Avatar, et cetera, he loves to say that he does the big picture movies so that he can fund his expeditions. In another life, he was definitely a scientist and engineer. Absolutely brilliant, brilliant person. And so I will not go into much detail on the human exploration side of that expedition today. It really was an incredible achievement and an amazing team. Coupled with the Deep Sea Challenger, we also had these two robotic vehicles, these robotic landers, each of which was about the size of a telephone booth. And we were able to drop these throughout the expedition at a few different sites and just leave them down there. Robots are much less fussy than humans in terms of you can leave them down for tens of hours if you want. And these landers, built in large part by Kevin Hardy, shown here, were just fantastic from the standpoint of science return. What I'm going to show you are a couple of videos from the deepest region in our ocean, where the pressures are comparable to Europa and the seafloors of some of these ocean worlds. And the videos that you'll be seeing are from cameras that are up here, and what you'll see in the foreground is this Niskin bottle, this water sampler, because after a certain amount of time, there's a burn wire here that then drops that arm onto the ground, and so you'll see that with a little color bar. And here's what we saw in the Challenger Deep, about 11 kilometers down. What you see in the deepest, darkest depths of our ocean is a lot of life. After a few hours of this thing sitting on the bottom, a few little specks came out of the abyss and started swimming around, and then dozens of them, then hundreds of them, and then up to a couple thousand of them. These creatures came out of the abyss to feed on this. I don't know if you can tell, but this is a fish head. And so this, we put in the net here and left it out as a baited trap to encourage some of these amphipods to come into this region and to eventually get trapped. Oh, well, let me show you what these guys look like. It's beautiful, but up close, these amphipods are not quite that pretty. They do look like something from one of Jim's movies. Inevitably, when I show this picture, somebody asks, what did they taste like? It turns out that one of the crew members actually grabbed one of those amphipods, threw it in his mouth and chewed on it and ate it. A couple minutes later, he went to the side of the boat and unceremoniously returned it to the ocean from which it came. But so as amazing as the amphipods were in the Challenger Deep, it sort of left us with the question of, well, what are those creatures eating when the fish heads are not there? And we think we got the answer to that question with a subsequent drop of the landers. In this video, you'll see that arm come down, and as it comes down, you'll see the background area of our landing site. And you see these rocks and a little dust up. Thankfully, some of this sediment drifted into this Niskin bottle here, and so I've done a lot of work on the few sediments that we gathered. When the dust cleared, this is what we saw. And geologists in the audience should be oohing and awing because this is outcrop, and never before had outcrop been seen at this depth. Coupled with that, when we zoomed in on the outcrop, we saw this. These, we have good reason to now say, are microbial mats that are feeding on the rocks, and we have good evidence that what they are doing is feeding off of rocks that are being altered via serpentinization. And so that same process that I described to you earlier of that sort of exothermic, slow, diffuse reaction occurring at Lost City is what we think is powering these microbial mats. This is about 20 centimeters across on that particular rock. And so these are a few centimeters in length, these filaments. And so so when the amphipods don't have that little fish head to chew on, and there's not enough marine snow, enough stuff falling in from above, they can perhaps go and feed on these microbial mats that are using the geochemical energy of the rocks from below. So it's with discoveries like this that I have some hope that the conditions at the base of Europa's ocean could in fact be habitable, if not inhabited. And so I'll close with just a few slides about the future of exploration. Cassini finished, and we currently have no mission that is greenlit to go back out to the Saturnian system. There's no mission currently planned to go to Enceladus. There is a mission that might go to Titan. It's called Dragonfly. It's in a competitive stage right now. It's PI'd by my friend and colleague Zibby Turtle out of the Applied Physics Lab. And it's an amazing mission that will hop around Titan if it's selected. For Europa, we have the Europa Clipper mission, which is being run and managed out of JPL with Bob Populardo as the project scientist, and an incredible team of PIs with many different instruments that will remotely sense Europa. This mission will fly by Europa some 45 times, mapping out the surface, taking images, doing ice-penetrating radar, doing spectroscopy, and it also has a couple of mass spectrometers on it, similar to what Cassini had. And so if there are plumes erupting from Europa, it could sample those plumes. I'm on this mission, but much of my time I spend, as David mentioned, focusing on getting the Europa lander mission concept to the launch pad. This is a mission that is in what we call pre-phase A stage. We hope to get it into phase A, sort of greenlit soon, and I won't quantify soon at this point. Just about a year ago, we released our science definition team report, and I'd encourage you to go and download this PDF. It's some 260 odd pages of very, very compelling reading. And I won't go through all of these bullets, but this is a mission that would land on the surface. It's battery powered, and its task would be to sample that surface material, sample some of that brownish, reddish material, ingest it into a suite of chemical analysis instruments that, in our case here, include a gas chromatograph, mass spectrometer, Raman spectrometer, and a microscope, to look for materials that could be potential biosignatures. It's a mission that could potentially get to the launch pad in 2025. In our mission concept, we launch on the Space Launch System, the big rocket that NASA is currently building. That allows us to get out to Jupiter in about 4.5 years. We then come down to the surface using a mini sky crane. If you're familiar with how the Mars Curiosity rover landed, we have a small version of that. Our lander is about half the mass of Curiosity. And Europa has no atmosphere, so we're able to do a pinpoint landing where our landing ellipse is about 200 meters in diameter. And then these sort of grasshopper legs allow us to land on the unknown surface of Europa, accommodating obstacles at the decimeter scale. The mission would last about a month. It allows for about 42.5 kilograms worth of science payload. It would sample a minimum of 3 times, possibly 5 or more times. And it would have this primary battery that allows us to iterate with scientists on the ground in the loop, being able to decide where to sample next. So in the best case scenario, if we start cutting metal tomorrow, we will land on the surface of Europa in the early 2030s. I've already been working on this mission for 10, 15 years. Again, this is not for the faint of heart. But it's an exciting time to be alive when it comes to the prospect of potentially finding life beyond Earth. And that leads me to my final slide, which, in my opinion, is one of the most compelling images ever collected from the history of solar system exploration. It's an image that was drawn by the hand of Galileo. And at the center is Jupiter, that wheel-like structure. And around Jupiter are these 4 points of light. And of course, when Galileo first turned his telescope up to Jupiter and saw these points of light, he thought that they were stars. He thought they were stars that he couldn't see with the naked eye. And so initially he just called them stars. Well, actually, he didn't just initially call them stars. He called them the stars of Medici because the Medici family was funding his research and Galileo was no idiot. But night after night, by tracking these points of light, he, of course, determined that they revolved around Jupiter. And with his careful tracking of Jupiter and of Venus and our moon, Galileo helped put the final nail in the coffin of Aristotelian cosmology, and he really opened the door to the Copernican revolution. The idea, of course, that the Earth goes around the sun is a star, the stars that we see could be suns to other planets. And in the decades that would follow Galileo, we would come to appreciate that the laws of physics, as we know and love them here on Earth, apply to worlds and wonders beyond Earth. And with the advent of spectroscopy and other instruments and tools, we will come to appreciate the principles of chemistry work not just here on Earth, but also on worlds and wonders beyond the Earth. And then with the advent of the space age and our robotic exploration of the solar system, we will come to appreciate that geology works beyond Earth. But when it comes to that fourth fundamental science, biology, when it comes to that bizarre and beautiful little phenomenon that we call life, we have yet to make that leap. We do not yet know if biology works beyond Earth. We have every reason to predict that it should and could and does, but we have yet to do that last great experiment. And so it's my hope that some 400 years from now, in much the same way that we can look back at the revolution that Galileo helped catalyze, it's my hope that 400 years from now, our descendants will look back at this time in the exploration of our solar system as the time when we did the experiments, we built the spacecraft, we sent them out there into our solar system and beyond, and made the great discoveries that potentially brought our universe to life. Thank you very much.